Okay, so let's continue where we ended yesterday. Let me remind you of this dramatic structure of the reasoning. Once again, the idea was that meta-empirical confirmation is an element of empirical confirmation in general, which becomes clear if we remember when one looks at the Bayesian representation of confirmation and tries to fully understand the basis, for the reasons for generating actual trust in a hypothesis in this Bayesian framework. And then the point was that empirical data can be partly or entirely replaced. Empirical data that confirms the theory can be replaced by more abstract considerations that are rooted in empirical confirmation of theories that get covered or unified by the given theory. But at the level of testing the theory, there is no empirical confirmation present, but just those requirements that the theory needs to represent those effective theories. And the same circle can then work and generate some degree of trust in that theory. And so the suggestion, of course, in light of our previous discussion, is that this provides a basis for understanding why scientists can legitimately have trust in hypotheses that are not conclusively or maybe not at all empirically confirmed at the present stage. Now, a few remarks on that first, and then I will specify quite briefly, but step by step for the various theories we have been discussing, how this plays out with respect to those specific theories. General consideration first, what is important about this approach is that the criteria that enter these considerations form a coherent whole, right? So they are observation. They are those arguments, the three arguments that I have introduced yesterday. They can be understood as predictions of the same hypothesis, of a hypothesis about the constraints on the spectrum of possible alternatives. So therefore, they can be mutually enforcing. So one of the argument can increase the significance of the other. And if we remember, what we understood from the start was that while the no alternatives argument itself, the no alternatives observation is the starting point, on its own it's not a significant argument. On its own there is no basis. If we just have an alternatives argument, we don't know what the significance is of that. And of course, if we think of no alternatives arguments in a broader spectrum, there are no alternatives arguments in various contexts, right? There are no alternatives arguments in rationalist philosophy, for example. The problem in rationalist philosophy is that those no alternatives arguments don't have any backup by other lines of reasoning. So it is up to the philosopher to judge on their own, based on their own thinking, whether they should take that to be significant or not, that no one has, on their opinion, found an alternative way to view this specific situation. So it is specific about the scientific context, not that there are no alternatives arguments, but the specific thing about science is that in the scientific context, one can use those other arguments as backups. And those other arguments are eventually based on observation, of course. In particular, the meta-inductive argument is based on observations in the research field. So if there is no confirmation of scientific theories at all, there is no significance of meta-empirical reasoning. It only works first, even in the absence of empirical confirmation of the given theory, it only works if these requirements are sufficiently well rooted in empirically confirmed theories, so you get empirical confirmation from there, and then you need a meta-inductive argument that is based on empirical confirmation elsewhere in the research field. So the entire thing only gets off the ground if it happens in a context where there is empirical confirmation, which means that it is also it broadens the prospects of generating credence in a theory, but it still relies on a constant stream of empirical testing somewhere in the vicinity in order not to lose control over those other arguments. So that is an important point. The second important point is that this only can be epistemically significant if this testing scheme, let's say, conceptual testing scheme, is critical in the sense that it cannot just confirm, but it can also disconfirm. So it's not biased towards confirmation, right? And this is the case with respect to all three of those arguments, and this is important. Otherwise, it would not have any empirical epistemic relevance. So if we think about those arguments and think about ways in which the corresponding kind of observation could actually decrease trust in the hypothesis, in the context of the no alternatives argument, there is a very straightforward way to do that, and that is to find alternatives. So if you have no alternatives to a theory and then you find some, that significantly, very substantially decreases credence in the given theory. First, because you have now conceived alternatives, and second, the fact that you found conceived alternatives while you thought you had an alternatives argument undermines the reasoning in favor of the previously postulated constraints. So one would infer from that the method of identifying an alternatives case is less reliable than one had thought. If one thinks about the meta-inductive argument, there is also a straightforward way in which this can lead to a decrease of trust in the hypothesis under scrutiny, and that would be if in the research field, in the domain where we try to get evidence of successful no alternatives cases, we get disconfirmation of theories that had been trusted based on meta-inductive reasoning. So to give an example, if we think about the situation before the discovery of the Higgs particle, as we said, the Higgs particle had been supported by a fairly strong no alternatives case. So there was meta-empirical reasoning that suggested that most probably the Higgs particle should be there even though it hadn't been observed. Now, if you imagine the situation that the Higgs particle had not shown up, so testing had ended with the conclusion, there is no Higgs particle. That would, of course, first have collapsed trust in the Higgs particle, but it would have done more than that based on at the level of meta-inductive reasoning. It would have undermined trust in the method that generated the no alternatives case in the Higgs case in the first place. So it would have undermined, at a more general level, trust in alternatives reasoning in that entire research context. So if you had been a string theorist who believed in string theory based on those kinds of reasoning that string theorists think, that there is no alternative to their approach, then after not finding the Higgs particle, there would have been the very urgent question, why do you think that you can have any trust in your no alternatives reasoning in the context of string theory if you weren't even able to understand the no alternative situation in a much more straightforward case of the Higgs particle? So it would have, not finding the Higgs on this basis would have significantly reduced credence in string theory. So what emerges if one thinks about this meta-empirical assessment is that credence is much more interconnected than it would seem at first glance. If something happens someplace else, it has an effect on credence in a given theory based on this meta-inductive structure, argumentative structure. If we think about unexpected explanation, there is also a way of reducing the significance of that. Of course, in the case of unexpected explanation, the disconfirming import is less symmetric than in the other cases, right? In the other cases, it is entirely symmetric. Don't find alternatives, increase credence. You find alternative, decrease credence. You find successful predictions of no alternatives cases, increase credence. You find unsuccessful cases, it decreases. Now, in the case of unexpected explanation, of course, not finding unexpected explanations anymore does not further increase credence, but it's not symmetric to finding them, right? So there is no symmetry in that respect. However, there is something that can happen, and that is if you find unexpected explanation and you attribute that to the uniqueness or to lack of alternatives to the given hypothesis that can explain all those various things, what might happen is that on a better understanding, it turns out that these connections are not dependent on the specific theory. They are due to some more fundamental underlying characteristic of the research context. So if that's the case, then one might argue, based on that more fundamental characteristic, there may, after all, be lots of, or several theories that can achieve this connection. So it is a less convincing argument in favor of lack of alternatives. And there are, yes, and this is not just a hypothetical thing, but there are cases where one may suspect that something of that at that level may be going on. So there are, in all three cases, with respect to all three arguments, there are those scenarios that actually reduce trust in the hypothesis. And of course, that's crucial to say that we observe at the meta level, and these observations can have an effect both ways on our credence in the hypothesis. Only on that basis we can be confident that this is not a biased method that is biased towards just collecting evidence in favor, but not being capable of collecting evidence against the hypothesis. So another point, or the second point I want to think about a little bit, is a charge against meta-empirical assessment that has been put forward. And this charge is that meta-empirical assessment is a method for further improving the status of the dominant research field. So it is an undue intervention in favor of what is the preferred approach anyway. So it is kind of it thereby might influence the situation in an unfair way. Let's put it that way. And two things can be said in that respect. First, this may be correct, right? I mean, these lines of reasoning, as I said, they are not self-fulfilling prophecies. So they may result in understanding that a theory merits credence, or they may result in the understanding that actually it does not. So it is not. It doesn't mean if there is the option of MEA, that it doesn't mean that MEA always works very well for a given theory. So there is a discussion needed between supporters of an MEA case in the given situation and opponents to a strong MEA case in the given situation. And it has to be discussed or assessed based on that discussion how strong the MEA case is. So it's not just a card you play and then you support the theory. It is a basis for assessing the theory. That is the first point. The second point is, of course, if there is a coherent case of meta-empirical confirmation in favor of a hypothesis, it does strengthen that hypothesis. And if it so happens that a majority of scientists implicitly, let's say, have come to the conclusion that this is the most promising research program based on those considerations, spelling out meta-empirical assessment makes explicit why they do so. So it therefore, in a sense, does reinforce the leading a dominant research program, which is justified in that case on this account. On the other hand, if it turns out actually that if you spell out a meta-empirical assessment case, it is actually weaker than one would expect, it can also reduce credence in principle in the hypothesis by spelling that out, by saying, okay, if you argue in favor of that, one would expect that there is a plausible no alternatives case, a plausible meta-induction case, and so on, in favor of this hypothesis. If one thinks about it carefully in those terms, that's not really the case. So it is not an automatism that it enforces the dominant research program. Yes?
So I'm curious, what is your criterion for when other programs besides strings should not be worked on anymore? What would give strings enough confirmation that you would say, fine, everything else is done?
I address to some extent this question, right in the next paragraph, so to say. So that's the first point. So there is potential reinforcement, and if one assumes that, let's say, one may share this assessment or one may not share the assessment, that the actual credence scientists have, or majority, let's say, of scientists have in a hypothesis is implicitly rooted in meta-empirical assessment, then spelling out meta-empirical assessment makes explicit why they do that, and therefore it strengthens their case. So to that extent, it is correct. Now the question, however, is what does that mean for the status of work on the other research programs? And there are two responses to that. First, let's say this is along the canonical line of thinking about these things, even if there is considerable credence in a hypothesis based on meta-empirical assessment. This credence will never be as strong or even close to being as strong as credence in a hypothesis that is empirically very well confirmed. No doubt about that. So there will be significant credence left to be attributed to other research programs. So epistemologically, there will be room left in most cases for work on other research programs. Of course, there may be cases where the case against the research program is very strong for consistency reasons and so on. But if that's the case, the crucial argument not to work on that research program doesn't have much to do with MEA, actually. It has to do with overwhelming reasons to think that this is not promising at all. So you,
I just want to make sure this is being recorded. Ricard says that empirical confirmation is in the end more important than meta-empirical confirmation.
yes, okay. Yes. I never left any doubt about that. There is another aspect, however, which I think is interesting, that is a motivation for working for proliferation, as Daniele Oriti calls this. That can be. It's not I'd say it's not probably a genuinely new aspect, but it's an aspect that can be brought out in a fairly convincing way in the context of meta-empirical assessment, which is that the no alternatives case in meta-empirical assessment is based on the observation that scientists have very seriously and consistently tried to find alternatives. Otherwise, if that's not the observation, if that's not happening, an alternatives case is not strong. It cannot be strong, right? If no one looks for alternatives, sure, they don't find them. Which means that trying to find alternative solutions and pursuing alternative solutions as far as to the extent one can find them is a crucial element itself of meta-empirical assessment. So meta-empirical assessment on that basis in a way explains why working on alternative research programs is of crucial importance even if they don't end up being successful. This has epistemic significance, high epistemic relevance, because it's the only way to understand whether the research program that ends up being considered the most promising one does have alternatives or not. So whether when credence in that hypothesis is merited. So meta-empirical assessment is by no means a line of reasoning that provides arguments against proliferation of thinking about a topic. Just the opposite. It relies on thinking about all possible approaches. Okay, so those were the general thoughts about this, or some general aspects. So let me ask you whether there are some comments or questions on that so far. Okay, so let's now look at the various theories and just very briefly sketch how a meta-empirical assessment or meta-empirical confirmation works. And in this case, I start with string theory because string theory is the one case where there is actually, let's say, a pure form of meta-empirical confirmation. So there is no empirical, quantitative, let's say, empirical confirmation of the theory, which means that the meta-empirical level must sustain or is the only support of credence in the theory. And in the case of string theory, there clearly is a strong case that is being made by string theorists, and one can spell out that no alternatives statement at two different levels. So there are many string theorists who, maybe most of them, in any case, let's say many, who take their approach to be the only promising approach for a theory of quantum gravity at all. So that, of course, is in conflict with what exponents of alternative research programs think, but string theorists aim at making that case. And on their understanding, their by themselves perceived success of these line of reasoning is a basis for credence in the hypothesis. Now, of course, as we discussed yesterday, this is slightly tricky business because most string theorists don't know that much about alternative research programs, so they rely on testimony. There are some string theorists who have quite very seriously thought of and learned about alternative approaches to quantum gravity, and their verdict is often taken as testimony by other string theorists. So that is the one level at which this plays out. And as I say, the point here is not to say, okay, just trust them. The point is that eventually theory assessment on that basis is a matter of discourse between the various groups. So if opponents to that position think that is misguided, there has to be a discussion on this, right? So it's a discussion process. It's not a declaration. The issue of making a no alternative statement. Then there is another level at which it is less contested that string theory doesn't have alternatives, and that is the level of not just of quantifying gravity, but the level of providing a coherent overall explanation of both what happens at the general relativity level and what happens at the level of gauge field theories. So to explain why gauge field theories, why these effective theories about microphysics are gauge field theories, and to explain why the one low energy limit is GR. And at that level, the string theory is the only approach that aims at answering that level at this point, which doesn't mean that other research programs don't have prospects of developing in that direction, but at this point it's clear that they don't constitute alternative theories in that respect. Yes?
Sorry, I didn't fully understand the first point, which is that when string theorists only take testimonies of their cohorts,
yeah.
Do you think that's should they have spent maybe a little more effort to learn how that? I mean, I don't know, quite frankly. I'm not sure about the optimal balance there. It is clear that these theories are, all of them are fairly complex and fairly difficult to understand in detail. So one might suggest that it may be helpful to have some degree of understanding of alternative context. One may also suggest that it would be better to have more understanding of alternative context. However, of course, the more you broader you are, the less focused you are on your own research context. So it is, I would say it's a difficult question where the optimal balance lies. And I wouldn't want to offer any let's say, recommendation on that. What I want to say, what I want to stress, however, is that in principle, the mechanism of relying on testimony of colleagues, researchers you trust, is kind of unavoidable in science. So, and it's a legitimate element of scientific reasoning. It happens all the time, right? You never, as a scientist in whatever field, you never know everything about your field. You know something from hearsay, and you trust that those people who tell you the situation know what they are talking about. So in principle, there is nothing to be said against this. The question is whether the number of witnesses or the density of witnesses is too thin, and that's a gradual question, let's say.
Yeah, that was exactly my question.
Yeah.
Not on individual level should a person spend more time to learn
Yes.
quantum gravity, but over the field, what is the balance of which have more general perspective?
Yeah. I mean, it seems clear that that there should be, there should be some points of connections where some exponents of the field that reach across the limits and allow first interaction between the fields and also allow an assessment of the other fields. Of course, once again, that also, I mean, if one looks into the details, that gets very difficult. There are lots of approaches, right? So there are approaches. So if one says, okay, each of those approaches needs to be grasped and compared by someone, at some stage this wouldn't work anymore. Yes.
So I am completely on board with you that most people in this community who know other programs, still think strings is better. But there are a few people I consider to be very credible and reputable and thoughtful who really know strings and really know some other programs. And like Ted Jacobson is a great example. So I don't want to put words in his mouth, but I'm just reporting a conversation a few years ago. We were talking about this, and he thinks strings is really interesting and should definitely be worked on, but he doesn't think it's as dominant or in the epistemic sense as blues. So I was curious, for you, what is the kind of role for there are very, very, very few people like that, I suspect, but and a lot more who just are endorsing strings. But there are a few people like that. So what is your view of their role? Do they provide slight disconfirmation, or should we just ignore them, or?
Yes, I would say that let's say the balance of opinions on this has an effect on what the credence in each of those hypotheses should be, and if that changes, or if that is different in different contexts, it does have an effect on the strength of an alternatives argument, on the strength of meta-empirical reasoning. So if one, for example, compares the situation string theory and versus other approaches to quantum gravity, and dark matter versus Mond, one might say that from it, let's say, one needs to distinguish between the individual assessment of an agent, let's say, who wants to have their own personal credence of the hypothesis, and that, let's say, this agent is an expert in one of those fields, and now they make up their mind. So they will assess their own research field in terms. So let's say they apply MEA now. So they assess their own research field in terms of what they understand in their field. So they would grasp the meta-inductive significance of the success context, success in the research context. They would assess unexpected explanation cases,
And depending on that, they would gauge their assessment. Then they also have this case, the NAA case itself, an alternative case. And in order to make that case, they need to first observe reasoning that comes from their own research field or out of their own research field, but they also need to observe the significance of statements from the opposing research fields, which they would need to consider less promising in order to have a plausible no alternatives case. So the more and the more convincing such reasonings are, the more that would affect their credence. And now, of course, in an ideal world, where that scientist is an expert on everything, they wouldn't care about those, right? They wouldn't rely on any testimony. They would say, I fully understand loop quantum gravity, I fully understand all other approaches, I fully understand string theory. So on that, sorry?
Were you just quoting David Brooks?
I don't think he ever claimed to be a big expert on loop quantum gravity. So the idea would be that on that basis you would not need testimony. If you feel that you are not sufficiently an expert in some of those fields, you need to rely on testimony. And of course, then the question is, what testimony is there of people you consider trustworthy? And that's then the crucial question.
Thank you.
So yes, so it's of course a complex story. So it is, yes. All right. So yes.
Are you sure that this is a merit of string theory? The fact that it is able to recover both general relativity and quantum field theory. In a sense, if we believe in an Aristotelic world that is with a lot of variety, different kind of stuff, and we see that when you should compactify string theory, you find a lot of different theories. So this is a sign that it is a bit too general, too powerful. So in a sense, it's like the notion of something in general that you can apply everywhere, and so string theory could be something similar or not. It is a possible objection.
I think, yes, I think it is a merit. And in particular, in the given context, it turns out to be a merit on my understanding. And this has to do with the issue of contingency with regard to those research projects. So this is my personal opinion quite clearly. But so my understanding is that there is a question in the absence of guidance by empirical data. There is a question how cogent what you do, what the project you pursue is. So how, to what extent you can make choices. And if you can make choices and empirical data doesn't tell you what is the right choice, I mean, this is exactly what Penrose says in this quote last time. If you can make choices and you don't have empirical control, it's very difficult to be strongly convinced that you have made the right choice. So it is one kind of trick of thinking about fundamental physics, one might say, to find an entry point that reduces the choices you can make. And if you compare string theory to other approaches to quantum gravity, that seems to be a substantial difference. String theory chooses an entry point that is very ambitious, that is a full coverage of everything, let's say, And other approaches or exponents of other approaches have criticized that. And that's too ambitious. You can't work this out. And it turns out, yes, it is, in a way, let's say, so ambitious that 5 decades of work haven't been sufficient to fully work it out. But then you look at the other approaches and say, okay, do you have a complete theory? And they don't. So it doesn't seem to make that much difference at that level, but it does, at this point, let's say, but it does make a difference when it comes to contingency. If your goal is a more reduced goal of quantizing gravity, you have various entry points, various starting points of how you can start thinking about the issue, and then you continue from there. And then it turns out that it's often difficult whether these different entry points then end up being physically different conceptions or whether they are different perspectives on the same conception and so on. So there is a lot of contingency that makes it more difficult to understand whether one is on the right track. And this highly ambitious entry point of string theory does the job that it removes those issues, right? With respect to the fundamental theory, there is never a choice. There is never a situation where you can say, okay, either we do it that way, and that will change the theory. Of course, there are lots of choices when it comes to the methodology of finding something out about string theory, which approximations you choose, and so on. But that's always understood to be an investigation into the very same theory. So it's just a method of understanding the theory, but there is no contingency with respect to the theory. And I think that's a merit of the theory, absolutely. So next step, let's apply unexpected explanation to string theory. And of course, what was the prime example, of unexpected explanation in the case of empirical confirmation does not work in the case of string theory because that was novel confirmation. And since there is no confirmation, there cannot be novel confirmation either. So this doesn't work, which means that according to the diagram we have seen last time, one needs to move towards unexpected explanation. And it's probably fair to say that these cases of unexpected explanation are constitute the main arguments for string theorists to have trust in their theory. They consider this web of unexpected explanation particularly impressive in their case. And just to give a flavor of what that is and what an unexpected explanation is as opposed to novel confirmation, just give 3 examples of various types, which are all fairly general examples, let's say. The first, the prime example probably, is the microphysical explanation of black hole entropy in terms of microstates in specific cases of black holes. Not the realistic cases, unfortunately, as always. But still, the fact that this works is remarkable. And it connects perspectives on the overall situation without the theory having been developed to that end. So when string theory was proposed, it was not proposed because people thought that's the most immediate, direct way of developing a theory of microstates about black hole entropy. And then they looked into it and they saw, yes, it works, right? Now, of course, if that's the viable theory about the Planck scale, it has to work. That's what you expect from such a theory. But you wouldn't expect it if it does not, right? Other examples would be the way the holographic principle, which has been conjectures based on general characteristics of quantum gravity,
plays out in a very nice and specific way and can be spelled out in a very specific way in the context of ADS CFT duality. Another example would be the way in which string theory can explain and can contextualize, let's say, another way in which gravity could be reached from a gauge field theoretical perspective. So one way of including gravity in a gauge field theory is to gauge supersymmetry, which then leads to what is called supergravity. And now it turns out that string theory first is supersymmetric, and second has supergravity as its effective theory. So it connects those approaches that may, at the first instance, seem to be potentially different approaches to the issue. So there is also a kind of an element of convergence in unexpected explanation, of conceptual convergence, let's say. Third, if we think about meta-empirical assessment, in the context of string theory, since string theory emerged from the quantum field theoretic way to think about physics, the meta-empirical argument would be mostly based on the success of quantum field theory. So one would point at an alternative cases that could be made in the context of gauge field theory and that eventually were successful. So, for example, you would have support for non-abelian gauge theory, for example, based on the observation that this can explain confinement. It seems to be the only plausible way to explain confinement, and it has other predictions that are not directly related to confinement. For example, that there are W and Z bosons that you should be able to discover. Based on an alternatives argument, you would have trust in that prediction. And then you test it and you see, yes, it's there, right? So that would be a successful alternatives case. Another one we have discussed already is the Higgs case, right? Where the standard model seemed to imply, based on an alternatives case, the existence of a Higgs particle, and then eventually it was discovered. So in the context of the standard model, there are several cases of successful alternatives cases. So the implication would be that physicists in that context of thinking about nature are capable of understanding the options and therefore are capable of understanding whether they should have trust in an alternatives case. Now, of course, on its own, that would be a questionable line of reasoning, presumably, because string theory is so different in so many respects to quantum field theory, four-dimensional quantum field theory, that is. But in conjunction with the other arguments, it does have significance, right? So in the case of string theory, it is important, it seems, that all three components of meta-empirical assessment are there. And all three are needed in order to make a plausible no alternatives case. And this is not always necessary, one needs to say. For example, if you think about the Higgs case and the no alternatives case in the Higgs case, there is no unexpected explanation argument there, because, as one often said, the Higgs hypothesis is an ad hoc hypothesis. It is introduced just in order to explain the mass spectrum in a reasonable way, and nothing beyond that. So there is nothing unexpected, no unexpected connection, at least at the level of standard model physics, with respect to the Higgs. So in the case of the Higgs, there was only a very plausible no alternative case based on scanning alternatives plus a meta-inductive case. And that was on its own enough, was sufficient for generating what was considered a fairly strong no alternatives case for the Higgs. In the case of string theory, two of the components would presumably not be enough to have a significant case, because all of those components on their own, or even two on their own, would be too unstable to make a convincing case. While all three of them, you have all three of them, and the question is how strong the alternatives case is based on all those three arguments. Okay, so that was, I think, yes, that was the discussion of strings. Are there any thoughts or questions about that? Yes.
Many questions. So about the first one, the slide with applying knife to string theory 1 was about the NIA, right? I was the second statement. You can go back. Okay, so here, first I think it is quite subjective to say that string theory explains something at high scales, for example. And for me, it looks like also that we are assuming that string theory is a potential theory, but we want to demonstrate it. Right? So it looks like we are assuming something that we want to prove.
Sorry, say it again. What do you think is assumed?
String theory is a good approach as a credible claim to explain photophysics, something like that. Right?
Yes, I mean, this is maybe formulated in a slightly misleading way. It's the only known approach, I should say. So that's the observation. The observation is, yes, known is missing here. So this is not the alternatives conclusion, but it's the alternatives observation. So the observation is we don't know any, we haven't found any others. And the question then is, can we infer from that there aren't any?
Okay, and we have a slide with 8. Here, also here, for me, it looks like it is quite subjective to say that these connections are meaningful, because there are no. For example, one I would add to the list, and I would prefer with respect to them, is, for example, that string theory can explain the number of generations of the fragments. Because this is a result, in a sense. But I would say that, for example, I don't know, holographic principle, it is a theoretical result, so it is not a meaningful connection. I might say that the holographic principle for me is wrong, for example.
Sure. I mean, the issue of explanatory interconnections is related to having credence in the significance of those observations. And one may not be sure about those, and they actually may be strengthened, credence in the significance of those observations may be strengthened by those interconnections also. So it's not about having the starting point, I'm absolutely sure that this is significant, or I'm absolutely sure that, that quantum gravity is holographic, but there are several indications that it is, and one would have some credence in the hypothesis on that basis. And that would be enough to make this significant, even though, of course, you are absolutely right. The question to what extent this is let's say the parts that are connected here are on their own well established as being significant, it's an issue. And arguably the case of black hole thermodynamics is considered the most stable of those cases. So it's most clear in that case that this is a significant statement. In the other cases, one may have doubts. With holography, one may have doubts. With supergravity, maybe if you don't already believe in string theory, maybe even more. You may say, sure, this is an option, but I don't think it is awfully trustworthy to start with. So if you embed this option, it may have some significance, but not that much. But the point is, those arguments may not all have on their own huge epistemic significance, but they do have some. And if you collect these interconnections, and you find lots of them in conjunction, they make a case. And then, of course, it's up to the individual observer to understand how strong that case then is altogether.
One last very quick
Yes.
concerning the third.
Okay.
Here, also the examples are, in my mind, we are trying to assess the annual theory, like the string theory, for example.
Mm-hmm.
And these two examples, in my viewpoint, is like the standard model, the framework in quantum theory was well tested, was really reliable at that stage. So my viewpoint is that we trusted all these, for example, the discovery of the Higgs particle and confinement, because the standard model was very well tested.
This goes for the Higgs model. So one can say before the discovery of the Higgs, the standard model was already well tested. With respect to the W and Z boson, that was not yet the case, right? So if you look at the situation in the mid-70s, there were first empirical confirmations were emerging, yes, it was not entirely clear whether this approach is the only one that can work, right? And the point there is, and let's say an important aspect of this is that there is, as we described, there is, let's say, a slippery slope from empirical confirmation to non-empirical. So the kinds of reasoning that apply are comparable. And so if one compares these two cases, one would say in the first case, if you look at the situation at the start of empirical confirmation of the theory, or let's say at the point when it was understood that this can describe confinement, there was some empirical confirmation quite clearly. So it's not the situation string theory found itself in. And there was the immediate implication of the gauge theoretical approach with respect to the existence of the W and Z boson. So it was weak empirical confirmation embedded in a significant no alternatives case, let's say. In the Higgs case, the issue is not the standard model per se, which at that point, let's say, is fully established. If we think about the situation, let's say in the 80s, after W and Z boson discovery, so the standard model is well established empirically. But the Higgs mechanism is kind of a module that is added to that. So the standard model in principle does not require a Higgs module. You don't need to have it in order to have all the other stories if it weren't for this particular empirical aspect that you want to explain. So it is a distinct question whether the Higgs particle exists, whether the Higgs mechanism is the right description of this or not. And so with respect to that question, what is going on here is not empirical confirmation, but it is a meta-empirical assessment. Yeah. All right. Yes, so let's have a brief look at the other theories. And in their cases, the situation is different because, as we have seen already, there is some degree of empirical support. So strictly speaking, what is at work here is not meta-empirical confirmation in the sense that the empirical confirmation is missing, but it is empirical confirmation that contains an element of meta-empirical assessment that is more conspicuous. I don't know why I wrote complicated here. What I wanted to write was conspicuous due to the limited power of the confirming evidence. So the meta-empirical assessment has a more prominent explicit role in the reasoning here. So applying MEA to inflation, for example, there has been this discussion on the status of inflation, and Ias et al., as we have described in earlier lectures, have denied the significance of empirical confirmation entirely. So they argue there is empirical data, but it does not, I mean, they don't discuss this in terms of confirmation, but they say it is not a substantial or significant empirical testing that is going on here. If one frames what they say in terms of a Bayesian account, they would be saying there is no significance of empirical testing, no significant empirical confirmation, because the individual models don't get substantial credence, given that there are so many of them, and the overall hypothesis doesn't get increased credence because the model building is so flexible that you basically can adapt inflation to any imaginable data set. So even if one takes that to be an exaggerated characterization, one may say that based on a canonical, straightforward understanding of empirical confirmation, there is an issue here. There is an issue as to how much credence scientists can have in inflation, given that empirical situation. And in that context, a meta-empirical perspective, or a focus on the meta-empirical aspects of theory confirmation, changes the understanding of the situation, because from a meta-empirical perspective, confirmation does not only work based on focusing on the strict predictive implication of the hypothesis of inflation. So what they in effect say is that the probability of the evidence given the hypothesis is very difficult to assess, because basically you can model everything based on the inflationary paradigm. So if there is something that doesn't look plausible based on the current models, you will say, okay, those models are now ruled out, but we can modify our approach in a way that we can account for that new data also. That's roughly their line of reasoning, which focuses on this element, probability of the evidence given the hypothesis. However, on our account, on the meta-empirical account, what is equally important to understand credence is the total probability of the evidence. So what can happen if additional evidence enters is that other options are being ruled out. So you can establish that it's less likely that there are any other options that can account for that data, while the inflationary paradigm still stands, so to say. So if you reduce the probability of the evidence on that basis, that also increases credence in the hypothesis. Therefore, from a meta-empirical assessment point of view, it is more plausible to have substantial credence in inflation based on the incoming data than from a straightforward empiricist perspective that does not take
the assessment of unconceived alternatives or conceived alternatives into account. If we apply a meta-empirical assessment to dark matter, we have already emphasized that the null alternatives argument is at the core of establishing the dark matter hypothesis. The point is, individual dark matter candidates have not been identified, but dark matter works, and the argument goes, nothing else does. Now, as long as no discovery of dark matter components is forthcoming, that will remain the crucial question. The crucial question will remain how strong the meta-empirical argument in favor of dark matter is, or the no alternatives argument in favor of dark matter is. If we apply meta-empirical assessment to grand unification, as we have said in the case of grand unification, there are no known alternative proposals, and the no alternatives argument on the basis of, due to the fact that this plays out within, let's say, well-known territory of quantum field theory, the no alternatives argument seems to be quite strong. If we apply meta-empirical assessment to supersymmetry, we need to distinguish between two different questions: supersymmetry at high energies and low energy or mid-energy supersymmetry. Supersymmetry at high energies is implied by string theory and gets credence from string theory on that basis, to the extent one has credence in string theory based on meta-empirical assessment. In the case of low energy supersymmetry, there are no good no alternative cases, as we have discussed. So each of the roles played by low energy supersymmetry can be taken over by other approaches. This was not the case for the separation of scale, for the naturalness argument, which was one reason why the naturalness argument was considered very, very important. Now the naturalness argument has been empirically rejected, let's say. Susie's role as a solution to the naturalness argument. Therefore, this is not an alternatives case in favor of Susie anymore. And in the other contexts, there are alternatives. So if one looks at supersymmetry, low energy supersymmetry gains credence based on empirical assessment, and the meta-empirical assessment only plays the supporting role it always plays when it comes to the significance of empirical data. So there, as always, there is a meta-empirical component, because that's an essential element of empirical confirmation, but there is no particularly strong element of meta-empirical assessment when it comes to low energy SUSY. So to conclude this part, to wrap up this entire issue of discussion of meta-empirical assessment, what I hope I established is that empirical confirmation can generate significant trust in our hypothesis only based on MEA. So MEA is required, is necessary in order to establish within a Bayesian framework that there is significance, there can be significant credence or significant increase of credence in a hypothesis. The very same strategies under certain conditions can be applied in the absence of empirical confirmation, and those conditions are conditions that are conducive to making an alternative, a plausible alternative case, even in the absence of empirical confirmation. And In such cases, meta-empirical assessment stands alone as supporting a hypothesis based on some criteria that are rooted in empirical data, but this empirical data is confirmatory for the theories that are covered by the new theory, therefore meta-empirical confirmation can generate trust even in the absence of empirical confirmation. So there is a wide spectrum of possibilities to apply confirmation arguments of confirmation, and those we have seen reach from cases of very high trust over cases of significant or moderate trust to cases where there is the cases of very high trust, of course, will be based on a strong case of empirical confirmation, but cases of significant or moderate trust can also be generated in the absence of empirical confirmation or in contexts where empirical confirmation is highly insufficient. And the basic structure of the reasoning that supports this, the meta-empirical structure in all of those cases, is the same. So this suggests that there is a basis for generating trust in a hypothesis in the absence of empirical confirmation or the absence of strong empirical confirmation, but acknowledging that there is this option to generate trust in such a hypothesis does not imply that all current theories merit strong support at that level. And whether they do, or to what extent they do, depends on the specific assessment of the individual case, the specific assessment at the scientific level, and therefore ideally should be the result of a discussion of those aspects and understanding of those aspects by all scientists involved in those issues. So that would be the idea. The final point would be that there are all those other aspects, that psychological aspects that are not epistemically significant, that arguably play a stronger role in the absence of sufficient empirical data than before. So this is a more volatile situation, and these aspects need to be taken into account and need to be addressed. However, there are also epistemically significant strategies to establish credence in those hypotheses. So there are those issues, but there is a core of epistemic significance that can justify that even though those theories have not found empirical confirmation or haven't found strong empirical confirmation, they are not just speculations. Yes, so that was all I wanted to say about that part. I have a last part about a quite different topic, about finality issues. And I want to say a little bit about that. I have too many slides, so I cannot fully present this, I think, but I think it's interesting to discuss it a little bit because it has interesting connections to this subject matter. Yes, so let's change the slides, and in the meantime, let me ask you whether there are questions about this part. Yes.
So I've seen some people like in social epistemology trying to frame the questions of consensus instead of it being about empirical adequacy or is sort of about, like, sort of it being about pursuit-worthiness. And I feel essentially like what's going on in physics, the question is about pursuit-worthiness. Like, I mean, from my experience with like string theorists, often they will say, even if they don't claim any sort of, or think of any sort of empirical adequacy, they will say, like, this is very fruitful mathematically, like this ABC correspondence, can help us condensed matter physics and stuff. So, do you think this picture changes if you want to sort of do this formal treatment of this sort of, how this mathematical analysis affects the conception of pursuit-worthiness? Because like in pursuit-worthiness, yes, the idea of current empirical adequacy or promising empirical adequacy takes place, but it's not the sole thing. So yeah, that's sort of one question. And the other question would be to sort of ask, so I think it seems to me at least that sort of the debate has sort of slightly changed the focus. So I think currently, effectively, so before it was like whether we're going to pursue this research project or that research project, or should string theory be allowed to be dominant. But now I think there has been huge budget cuts to theoretical physics generally, and in the US, for example, the most grants have been cut specifically to physics, right?
Yeah.
So the debate sort of shifts towards the question of should we finance any of this?
Yeah. Yeah.
And there have been also philosophers, physicists that have suggested sort of maybe not very explicitly, but I've heard some of it like suggesting that don't fund this at all, like just fund condensed matter physics, something else. So does this sort of shift the sort of the way we want to sort of provide this rational reconstruction of these considerations?
Yes, yeah, that's an important issue, and the comparison between pursuit-worthiness and credence in the hypothesis, so judging the probability that the hypothesis is viable, is a very important one. In particular, it is important due to the current general situation science finds itself in, where there are, on the one hand, or let's say more specifically, fundamental physics finds itself in, where on the one hand there are increasing constraints on financing science at all, and on the other hand there are increasing requirements with respect to the investments needed to develop experiments in fundamental physics. So the situation gets in two ways more complicated. So in the end, funding decisions and research decisions increasingly have a very strong aspect of questioning the pursuit-worthiness, because there is this selection, and in selection of research programs, and in selecting that, all sorts of considerations enter. So one consideration would be: should we be interested at all in fundamental physics? Should we, if there is no prospect of technical utilization, should we do that at all? And of course, that's a very grand discussion, right? I mean, I'm personally very strongly on the side of arguing that the pragmatic utilization ideology of everything is highly misguided, and one should keep the principle of knowledge as a very important goal in scientific investigation. But of course, that's a debate at a very high level of abstract reasoning about goals and the meaning of life, if you want, and things like that. So, all right. So that's the first part. The second point is that this meta-empirical assessment is
decidedly not about pursuit-worthiness to the extent it goes beyond credence. It is explicitly about credence, and it can only be formulated about credence, right? It is, if you try to formulate it in, formalize discussions about pursuit-worthiness, the formal structure of the reasoning is entirely different, right? There is no 0 to 100% pursuit-worthiness, right? There is no probability of pursuit-worthiness, but this is a probabilistic approach. So there is a probability of a theory being viable, and that probability can be between 0 and 1. So already the starting point implies that this is not about pursuit-worthiness per se, it is about credence. And now, of course, credence plays an important role for pursuit-worthiness, but it plays a role that is embedded in other considerations. It is embedded in the consideration, for example, how important it is at all to find out what the fundamental laws of physics are, for example. It is embedded in consideration how much money do we need to empirically test that theory. So, however, the question of credence in a hypothesis nevertheless plays a very important role, because if I say that, I don't know, a certain percentage of the research budget in fundamental physics or in experimental physics, let's say, has to be invested in experiments to test this, and then the question is this hypothesis, and then the question is, okay, so what is the probability that this is viable? And you say, well, the probability is maybe 2%, then you would say, well, I mean, a lot of money to test something that's most probably not viable anyway. If you say it is 50%, it's a different story. So of course, credence plays a very important role, but it doesn't play the only role in research decisions. And very clearly, the status of this is that this can contribute the viability part in that equation, but it does not go beyond that. It is not, I mean, there have been suggestions to frame meta-empirical assessment in terms of pursuit-worthiness, but on my understanding that just doesn't work. It is it's based on a misunderstanding of what the reasoning does here. It is explicitly probabilistic and therefore explicitly epistemic. Yes.
May I ask something about a quantitative or at least comparative evaluation of meta-empirical confirmation? In the sense, do you think that in presence only of meta-empirical confirmation is possible to believe rationally that a theory is more probable than not that it is true?
Yes, I think so. I think so. I think that, I mean, my own assessment, I mean, as we said, truth is a complicated concept, but if I talk about viability, my personal understanding would be that or let's say my personal credence in string theory would lie substantially above 50%, for example. And that's about the theory without any empirical confirmation. Yeah. Yes. So I don't think that these credences need to be particularly low. They can't be very high, right? So it would not be plausible to go up to, I don't know, 99% and say, I'm pretty sure that wouldn't make sense. I mean, of course, these are just very rough estimates anyway, or not. There are no specific numbers, but I think it's fair to say that it's not anywhere near an empirically well-confirmed theory on the one hand, but it is at above 50% on my understanding, and that I think that's compatible with the constraints of the method. Yes.
Yeah. So just a bit of reply. So In some papers, like on this, you have discussed how you want to stress that the credence which you assign to a theory is not necessarily linked to truth, because like this sort of assumes certain realist stances towards the theory, and instead it's about empirical adequacy. Like we assess our credence in whether this theory is sort of, in a final sense, empirically adequate. But then there is this thing where we have like empirical adequacy sort of is or should be like a practical term. Like we know now whether our theories, like to what extent it's empirically adequate for the empirical results we have right now. So then it just seemed to me that there is this duality where you sort of we have this practical notion, accessible sort of meta-empirical notion of empirical adequacy, which we can assess right now, and which is sort of, in a sense, alone about these theories. And then there is this sort of promise of empirical adequacy, which can be sort of increased, or final empirical adequacy, which can be sort of increased by meta-empirical consideration. So, in that sense, like, and some, as I said, like social epistemologists, when they analyze pursuit worthiness, they're not even going like to talk about pursuit worthiness outside of epistemic category. So like they consider pursuit worthiness as the promise of empirical adequacy. So in that sense, I found sort of this account of sort of this future empirical adequacy, or promising it, or the credence of like final empirical adequacy sort of fits nicely with this sort of epistemic, like just epistemic part of pursuit worthiness.
Yeah, I mean, so two things. First, I prefer not talking about empirical adequacy with respect to what is tested here, because of course empirical adequacy is something that can be handled in a very flexible way, right? So I can say this: my theory is empirically adequate, given the data I've collected. While the characteristic that one aims at when testing a theory or understanding a probabilistic assessment would need to have a more universal criterion than that. It would not be total empirical adequacy under all imaginable empirical tests, but it would not be a specific data set either. So one concept that I think is helpful to think about this is the concept of an empirical horizon, for example. So you talk about everything that you can test within certain limits, let's say. So the important thing that this is a fairly strong statement already, to say that the theory won't ever be in contradiction with data within this empirical horizon. So that is the aspect of viability. When it comes to the epistemic aspect, or the issue of prospects of epistemic significance of a theory in the context of pursuit worthiness, there are some aspects. Of course, there are quite some aspects that are covered by this. So clearly, pursuit worthiness includes considerations of this kind. But even if one just focuses on epistemically significant considerations, the understanding in the context of pursuit worthiness is a little broader. So, for example, in pursuit worthiness, a theory on that account is considered pursuit worthy if it is known to be false, but it is expected to lead scientists towards another theory that then can be viable. That is a complicated consideration. It's difficult to quantify what one means, but it's clear that this happens in science. This is important. And in science, there are lots of toy models, of thinking within context of unrealistic scenarios for exactly that reason. And that's pursuit worthy, and there is an epistemic reason for that. And the epistemic reason is that these theories, working on these theories, is understood to be conducive to finding an empirically viable theory later on. This, however, this is epistemically significant, but it's not covered here, right? The credence in that theory, nevertheless, is 0. So if I apply this methodology to this, the response would be the credence is 0, which does not mean that I should not do that, because it can be helpful, and the broader context of pursuit worthiness can explain to me, can tell me why. But it's a different approach. So this is a fairly specific approach that points at the credence in a specific hypothesis. So yes, so that's the constellation. Yes.
Can one think about your approach in this big movement inside the philosophy of science at the beginning of the 30s, in which the notion of verification that was at the beginning became a confirmation, testability and meaning, and after a certain point both Carnap and Hempel make a sort of new point of view in which confirmation is something very, very generic, strongly theoretical in the 50s, the 50s. In a sense, that in this direction you make a step forward in the sense that now confirmation could be also something intertheoretic, not only in the sense that you have evidence and theoretical notion and theoretical sentences that could be very far from evidence, and they are confirmed indirectly by the theoretical network. And this was the last position by Carnap and Hempel. In a sense, your point of view is a step forward in the sense that other theories that are connected with the theory in object could be confirmed through evidence in this larger sense. It's possible to think in this perspective.
I think so. Yes, I think so. I think that, so clearly there is let's say, continuity or connection between the thinking of late Carnap and Bayesian epistemology. I would think, I mean, I'm not really an expert on the late Carnap, but it seems to me, to the extent I understand what he's doing, there is exactly this problem he faces, that it is so difficult to come up with a specification of probability as long as one focuses on this narrow connection, empirical data and prediction of the theory. And that was, to the best of my understanding, that was an issue for Carnap when developing this. And it is an issue also in the Bayesian context, right, where there are those discussions of consistent treatment of the catch-all hypothesis, for example. And all these considerations, these problems, push towards a more formal and less applied understanding of this probabilistic reasoning. So it pushes towards understanding this probabilistic reasoning kind of as a placeholder, where you don't take the probabilities seriously themselves, but you use them in order to reveal the argumentative structure of the reasoning. And that is, in a sense, what happens in the late Carnap, I think, and then in a sense it's also what happens in canonical Bayesian epistemology. And yet you're absolutely right that the attempt here is to go beyond that, to add a... Right, exactly, absolutely.
And probably in general, physics is going in this direction, because it's more and more abstract, more and more general, and so there is something also from an historical point of view, this is that new physics is different from the physics of the first half of the 20th century.
Mm-hmm.
We need perhaps
Yeah,
this kind of...
yeah, right, exactly. Yes. Okay, any further questions or comments?
All right, so then let me say a little bit about finality. I only have 12 minutes, it seems. So I don't know how to do that now in the best way. So let me just step in and say a little bit about this. So the point is that final theory claims they were an essential part of the way physics was understood up to the 19th century, let's say. So Newtonian physics, for example, was understood by most physicists to be a final theory, as was Maxwell in the late 19th century. In the 20th century, the revolutions induced by quantum mechanics and the theories of relativity quite substantially reduced the appeal of final theory claims. And there was kind of a resurgence of final theory claims in the context of string theory due to some arguments that pointed at the finality of string theory. And this is it is an interesting situation because, of course, on the face of it, string theory is a very weird theory to have a finality commitment to, right? It's a strange case of finality claim if you compare it to Newton. If you think about Newton theory was empirically hugely successful. And one reason why people thought it would be final was that it was so successful for a long period of time that people thought, okay, so that's probably it, right? It is an inductive reasoning, a meta-inductive reasoning, saying that it's here for so long and it works perfectly in all contexts. So that's the true theory. And then there was also, of course, a kind of an alternative reasoning in favor of that theory. Now, in the case of string theory, we don't have an empirically confirmed theory at all. And it has not even, as we discussed, not even come close to a full formulation. So it's strange that you say, okay, Newton's theory that had all these very attractive features was not, and initially we thought, okay, if Newton failed, then probably it makes no sense to have to make final theory claims about any theory. And now here comes these highly incomplete, empirically unconfirmed theories, and there people say, okay, but this is final. So the point about this, about the final theory claims regarding string theory, is that the argumentative mechanism for finality works in an entirely different way here. And I may just stick to that slide for time reasons and say a little bit about it. There are three ways of reason in favor of finality in the context of string theory. First, the first reason focuses on the fact that string theory covers all known phenomena and actually conceptually doesn't provide a basis for being embedded in a more fundamental theory. So it does what one might expect from a final theory if one thinks that a final theory should be universal, should be unified, should cover all phenomena. And more than that, it also represents a conceptual endpoint because it cannot be extended beyond what it is.